related to the calculation of structure constant of single trace operators in planar and equal to 4 superior mills. So it's perfectly in the theme of the conference. It has to do, of course, with gauge and string theory, and it's the most prototypal example of an integrable gauge and string theory pair that we know of. But despite integrability, we don't yet have a clear solution to this problem. So the question, as I say, the main question for the talk is, can we calculate structure constant for this local single trace operator at any value of the Toft coupling? So of course, it is something we can do more or less easily, I would say. Less, I mean, it's not that simple, but it's doable at weak coupling by calculating all the planar graphs that are ending on 3 local operators. So here the operators are, I think I can point. Okay, what is this? Okay, sorry, I did not realize I have. It's better with the mouse? Okay. Okay. Ah, sorry, yes. Sorry, it's right, okay. Okay, sorry about it. So we represent local operators by, these are composite operators which are single trace. So we represent them as a spin chain of this type. And what we have to do in order to calculate structure constant of 3 of these operators in perturbation theory at weak coupling is to essentially draw the weak contraction that are planar, that we can draw on the sphere, and calculate all the possible correction loop by loop. Okay, so that's a difficult problem, but there are techniques. It's a null problem, of course, to calculate Feynman diagrams in gauge theories, and there are techniques. And in the opposite limit, at strong coupling, we have another description, which is in terms of this pair of bounds, which is describing the splitting of the string. Okay, and there is this mapping that we are familiar with between operator on one side and string state on the other side. And the question, of course, is try to understand if we can have try to see if we can have formalisms, formulas, say, that give us the structure constant at any value of the coupling using integrability in between. So the best we can hope for is that, presumably, is that the solution, if it exists, is as good as the one we have for the spectrum of scaling dimension. So I won't say much about this problem. I'm assuming you're a little bit familiar with it. Of course, it has to do with diagonalizing dilatation operator of the theory that we can map to spin chain Hamiltonian in the spin chain picture, which proves to be integrable. And the solution is known in one form. I presume some people will be talking about this solution during the conference at some point. And if it is not as good as a solution for the spectrum, so perhaps at least we could expect that it is in principle complete, that we have achieved something and write a formula that is in principle enough to contain all of the information at weak and at strong coupling, okay, and at intermediate coupling, of course. So the hexagon method, which is the one I will be talking about here and elaborating on, is the beginning of an answer. It's a way of approaching the problem of calculating this pair of points diagram using integrability. And it's getting a lot of the solution, I would say. In some situation, it might also be getting all of it, although perhaps not in the context of structure constant, but of higher point function. But it is also known that it faces difficulties for short operators. So if you ask a question about like your favorite operator, like usually Konishi, like just length 2 operator with a few excitation, then we sooner or later we run into problem and contradiction that we must solve. And they are directly related to wrapping effect, which were also a problem for the spectrum for many years before it was solved. So the question, the more concrete question, I guess, that I will try to answer in a way, or perhaps just try to guess a solution, is to find a kind of UV completion. By UV completion, I mean here something that starts from the hexagons and add the infinite tower of wrapping corrections that are needed to get the full answer. Okay. might not be the solution, the best solution we may find, or that may exist, but at least it is possibly a solution. Okay, next. There is no next. This one, sorry. So what are the hexagons? So they are building blocks for correlation function. As long as we restrict ourselves to single trace operators, then we believe we can construct any sort of worldsheet, planar worldsheet, or with handles and so on, with any number of punctures using them. Of course, the more, I mean, when the geometry gets complicated, we need to get together a lot of hexagons. But for the structure constant, we only need 2 hexagons, and they arise when we think about cut opening this pair of pants along the SYM. So here, for instance, we have 3 SYM, green, blue, and red. And by cutting opening around, along this line, what we get is an hexagon in the front and another hexagon in the back. Okay. And these objects are simpler because they don't have boundaries. Okay, so they can be defined asymptotically, and so they are subject to all sorts of integrable bootstrap approach. They're also giving us the answer for very long operators. So this factorization between the front and the back is precisely what we expect when the SYM are very thick. So which is so typically for long operators. We'll get a lot of contractions. Structure constant, we only need 2 hexagons, and they arise when we then the factorization is strict in this asymptotic limit for long operators. And so by knowing the hexagons, or to be precise, the hexagon form factors, we actually know the answer in this regime. Okay. So as I say, these are objects we can bootstrap, and there is actually a conjecture for them, to our loops. And just to give you an idea about what they are just some sort of amplitudes for creation and or absorption of magnons. So here is an example with 2 magnons at the bottom here on some piece of an operator, this operator. And there is no other magnon on the picture, so we can think that these states are just creating in some asymptotics here and absorbed by the geometry. And that is possible because the hexagon do not preserve the energy of the magnon, and so can absorb or particle or create some. But the difficulty then is to recover the finite length in the problem. So we find simplification, of course, by sending the length to infinity, but eventually we are mostly interested in physical operator, which have finite length, like Konishi that I mentioned before. And there is a problem of gluing. The hexagon back together by essentially geometrically identifying edges that has to disappear when the geometry is closed. And the recipe is to sum over a complete basis of mirror magnon or mirror state on each SYM. This is what we use as a glue. So in the same way, if you've never heard about this mirror magnons, well, let me just explain quickly. So in the same way that we can have magnons on the physical edges, here, for instance, at the bottom, which are the operators in the theory, we can have magnon on the virtual dash edges by doing an analytic continuation, which is kind of a crossing transformation, or to be precise, half a crossing transformation. They live in the so-called mirror kinematics, which is a little bit virtual. So they are not, strictly speaking, observables, because they are not excitation on physical operators. And they are essentially just used to glue things together, you know. And so in the end, we always want to integrate them out, because they are just some of the intermediate states. So schematically, what we get is this type of representation for the structure constant, where we sum over the insertion of any number of mirror magnons on each pair of edges. Of course, there is a matching condition. Whatever we put here, we should have on the matching side here. And we should sum over all the possible states and weight with the energy. So whenever a particle crosses a channel, there is a weight to pay, which is controlled by the energy of the state. And naively, this is accounting for all the finite size correction on the geometry, because we are summing over every possible channel. So in principle, we are not missing any information. We should be reconstructing the geometry entirely. And it works pretty well, especially at weak coupling, where the mirror effect, which I've just mentioned, this infinite sum, actually truncate in perturbation theory. So that is so because producing this virtual excitation is a bit like producing, you know, some virtual exchange of virtual gluon or scalar particle in the theory. So it is suppressed with the coupling. So in particular, here I'm just taking the situation with the Konishi and two short-length BPS operator for the counting. So what we have when we have no mirror, the process, for instance, with no mirror magnon contribute at 3 level, as one would presumably expect. And as we start adding excitation on the edges, we see that we pay 2-loop suppression factor, 3-loop, and so on. Okay. So in particular, if we want to do calculation of 3-loop, we can just stop here. We just add them up, add up all of these 3 contributions, and we are done. This is so up to this wrapping order when we show up at 4-loop in this case, and which is associated to situation where we have magnon on both sides of the picture, which are facing each other. So if we write the integrand for such a process, what we'll find is that there is a pole at coinciding rapidities when u is equal to v, which is precisely when the two guys have the same quantum numbers. This is a kinematic, this is a sub-kinematic, so this is twofold kinematic, for which is describing a magnon that is going closely around the local operator. So it's a magnon that is going straight on the geometry without really interacting with it, which means in fact that it is very close to this operator here at the bottom. So that's a sub manifold of wrapping configuration, and it is, as I just said, attached to the operator. But it's a problem for us because it is divergent. So there is nothing we can do to integrate the integrand at this place where u is equal to v, and so we have to do something. But we don't want to throw all the formalisms away because of that. We are clearly capturing a lot of the answer. So what we want is essentially a recipe to remove the divergences and add the correction that must be added to the hexagon formalisms to get the right answer. Yes?
So, but what is the physics of this divergence? So is the hexagon formalism which is not perfect, or you think it's just the fact that you don't consider something inside the hexagon formalism?
I'm not sure I fully understood. So the physics, so they are just renormalization effects from the point of view of the field theory. But of course, they are not the only renormalization effect. You know, the mixing problem started before wrapping in this theory. But somehow everything that is below wrapping is well captured by the asymptotic description and is in a sense not problematic in this formalism. But as soon as we try to capture or to include these new contributions that are divergent, this renormalization effect, then we pay the price that we must renormalize them before. So the problem just gets worse at higher orders, and it's actually plaguing, the divergences are plaguing infinitely many graphs. So here I'm just giving an example with more magnons being involved. And of course, whenever you have something that can form a loop, you will get a problem. And the problem will get doubled when you get the possibility of forming 2 loops and so on and so forth. Okay. So it's really a hierarchy of problems that one has to solve for and resolve. So the plan for the rest of the talk is to first describe what type of handle we have on this problem. How can we hope to solve it and include this wrapping correction? Get then some expression for wrappings at leading order for the simplest structure constant that suffer from this problem. And from these insights, try to get some conjectures and do checks. Okay, that's the idea. So the problem is actually quite old, as I say. It's also there, in fact, for the spectrum. It has to do with the fact that in infinite volume we have infinite volume. Sorry, observable will receive finite size correction. So whatever solution of a problem in finite volume we are considering, it must incorporate wrapping correction, which are typically exponentially small in the length for gap models, so they can be ignored for asymptotically large volume, of course. And they are naturally seen as arising from virtual excitation or this mirror magnon against that are winding around a circle of length L. So in the case of the cylinder, there is a trick that helps capturing them easily and analyzing them, which has to do with turning the picture around and mapping the circle here to a thermal circle. So the problem becomes the one of calculating some quantity observable at finite temperature with a temperature that is inversely proportional to the length. And in this context, the sum of our wrapping correction, which might still be a little bit nebulous so far, just becomes the sum over the state, the regular trace. Because of the circle, we take a trace over the state of the theory, which here is this mirror theory that lives in this orthogonal channel, not the original spin chain. And the regularization is also implicitly there because we will have divergences if we can calculate something like a trace in infinite volume on a cylinder. Just because we have an infinite volume, we typically get volume contributions that are divergent. But there is a natural regularization that people naturally switch on without sometimes even mentioning it, which is to replace a cylinder by a torus of large width R, which is not related to the original length L. It is this other direction here. And we take it to be very, very big. In particular, if we're interested in calculating the energy of the state in finite volume, then we just get the equivalent problem of finding the free energy density at a temperature 1 over L in this mirror theory. Okay, just again by turning the picture around. And that is something you could calculate you could get from the partition function by just summing over all the loops. Okay. But with integrability, we can do better. And this is just to introduce some letters and notation. And we can write a TBA. So when we have a lot of information about the theory, like the exact S matrix and so on, the particle spectrum, and we can immediately go to some thermodynamical argument to derive a set of equations that is controlling the free energy density. And what we get are this famous TBA equation for this Y function, which essentially capture correction to the weight of a particle with an energy E, okay, which is conjugate to this length. Okay, and they are what they are. And when you know them, you can just calculate the energy level of the theory in finite volume. Okay, it's just like a one-line formula. It can get more complicated, of course, when you have infinitely many Y's, but it is known in principle. Moreover, you can get generalization to excited state as well. So if you're interested, as it is the case for us, not in the vacuum, but in state which have magnons, then you can play a nice analytic continuation trick, which adds singularity in the problem that will eventually translate into magnons in the physical picture. And you can reproduce typically the formulas that you could get asymptotically using Bateranzat's argument, as well as the infinite tower of correction, which is of course the main point here, to be capable of controlling this wrapping corrections. So the problem is essentially the same. I mean, the physics of the problem is essentially the same for the structure constant, and perhaps this is answering a little bit better your question. Namely, they are coming because of this infinite volume that we have in the mirror direction when we approach a physical age, which is, strictly speaking, asymptotically far away. So we could imagine just removing this volume or cutting it off by putting two structure constants together like that, and considering some genus to surface. See if something can be calculated here using integrability, and possibly by some by some fancy analytic continuation, get some structure constant out of it. But there is a picture that is nice to draw, but not very useful in practice. At least I don't know even the beginning of an answer for how to calculate this type of thing. So we can go to another class of problem, which is not exactly in the same universality class, but very closely related, which has to do with the calculation of form factors of local operator in integrable theory in finite volume. So here I will only consider the simplest situation with two protected operator and one non-protected one. So non-protected one here mapping to states with magnon, the other one being just like vacua of the theory. So the interesting observation we could make here is that it is enough to cut only once the structure constant to get something finite. By cutting once, we are cutting all the divergent loop in the problem, because the only remaining loop that we have are the one here encircling the BPS operator. And that one, we expect them to vanish. We expect because of the operator being protected and supersymmetric, we don't expect any correction here. Well, at least we believe we don't have to worry about the divergences here. There are divergence, but they are multiplied by a big zero. So after doing that, what we get is, at least at the cartoon level, very similar to the calculation or to the picture we will draw for the form factor of a two-dimensional operator. So our operator is this thing here in the middle, and the state are whatever is incoming and outgoing in this picture. So whatever state we choose here and there. Okay. And of course, that is not new. That's something that people often invoke, this mapping to state and operator to approach the problem. And it has appeared before in some study, parallel study, and that is not an exhaustive list. So just to can flash here the problems that we face. So here again, we have this problem of volume effect. So what I did here is that I took the picture, I removed the excitation just for simplicity, and then I turn it around just to put the mirror channel here along the horizontal axis. What we want to do is to wrap this figure. But as we said before, we have infinities here at the two boundaries because we have an infinite volume. And they are manifest in a way in the singularity, in the kinematical singularity of this matrix element. So we have this operator BPS. It is absorbing a U and returning a V here. And when we look at what happens when U is close to V, we find some universal divergence or pole, which are essentially associated to the path that the particle can choose to go from bottom to top, very close to this boundary. So here, if it is propagating close to this boundary on the left, it will pick a factor exponential minus the red length, because here there is some thickness, times the energy and this pole. And similarly, if we go to the right, okay? So clearly we cannot take the trace or take the limit, identify U and V here precisely because we have these singularities, okay? It's pretty clear. And it is similar to what we find for the form factor of local operators. So in a local QFT, local QFT, sorry, if you really think about this as being local. In this case, the situation is left-right symmetrical when the operator is strictly local, if it has no string attached to it, for instance. And so and there is no thickness as well. And so these two guys add up together to give a delta function, okay? And the piece that people will consider as a finite piece, the finite part in the problem will be the connected part behind, which will be smooth in the limit when theta goes to theta prime. So as I said, it's not possible to trace over delta function normalized state. So what we have to do in practice is again switch on some IR cutoff and try to do the algebra with the operator being included. And that is related to putting a local insertion on a torus and calculated this trace. And that is a problem that has been studied for many years. And the formula is known in this case and give a good example of what we may expect to find also in the case of the hexagons. Namely, what was found, or first conjecture and then proved later on, is that the finite temperature one-point function admit indeed a form factor expansion in terms of diagonal form factors, or at least some suitably defined notion of connected part of this form factor, which is finite, and some factor here which are more complicated and depend on the y function of the theory, and that encode or resum in a way all this wrapping effect. So that is essentially separating the physics between the operator and the effect that we know should be there just because we have this wrapping divergences that we must subtract. And this type of formula can also be generalized to excited state, if at least for the so-called for the diagonal matrix element. So if the state, the incoming and outgoing state are the same. So that is something to well, we can try to draw inspiration from this formula and for the hexagons. Of course, our case is not exactly diagonal. In fact, well, we can engineer something diagonal, but typically it's very complicated, so it's not clear whether we want to study them in a lot of detail. It's the simplest case are closer to non-diagonal matrix elements, for which we don't have yet Leclerc-Musardo formula. We do have some piece of information, in particular from the work of Zoli and collaborators, but we don't have the full answer. But we can, here I just wanted to mention that we can still make some progress as far as the IA expansion is concerned. So if you want to get information about the wrapping order by order, wrapping by wrapping, not try to aim directly at the full formula, then we can make progress algorithmically by using a kind of diagonalization process. So the idea is to make the picture diagonal by embedding the object we want to study in a higher point function. And then that will generate some distances. Sorry, that will, yeah. We will have to introduce distances in the problem, of course. That's a more complicated object. and by playing with these distances, like taking like some large separation limit, we will eventually be able to extract the piece of information with the non-diagonal form factor out of the diagonal one. It's an idea that was followed by Zoli and other in the past. It's not a novelty, but here we were using it in a slightly different way by putting excitation on the outer boundary instead of trying to extract them from the middle. So we are trying to get non-diagonal matrix element by putting excitation from the beginning on the outer boundary that we have under control.
I don't have the user. I don't quite understand. The blue line
is the blue line? No, it's just the bridge. Sorry, it's just representing the bridge between the two.
I mean, this cut, are you summing over states or?
Here in the middle?
Yeah, they're very
here?
Yeah, is there a sum over states? Like
so in principle, there is a sum over states, but of course, in the large sigma, at large separation, if we're only interested in the leading term, it's only the vacuum contributing, yes. And here, well, here we are cutting first in the back to get actually, do I have a figure? Not quite, sorry. So we are cutting in the back and also taking a large separation.
Yeah, somehow I don't want to see, I'm not sure I understand why only the vacuum contributes, because anytime you have identical states contribute.
No, the vacuum will dominate, sorry, in at large separation. I'm not saying that. Yeah. Yeah, well, okay, we can, I don't know, maybe I did not get it, or maybe I forgot some details. Anyway, the good point here is that since we have something that is diagonal, we can apply the connected prescription and also the generalized Leclerc-Musardo formula to this object. And by sending the separation to infinity, then get something out of it for the object we're interested in, like this half here. Which is free of divergences. Just by construction, the divergences here will be automatically removed. In particular, it's not, I mean, it's not very difficult to implement it in simplest cases where we have, for instance, a single wrapping that can form, like here with a single, imagine cutting on the left. So if I have a single particle green, a single green particle here, then it's clear that I can get at most one loop going from side to side here. Okay. And the prescription to get something finite is to shift the incoming and outgoing rapidity here by some epsilon before identifying them. Okay. It agrees with earlier formula that was obtained with a more heuristic argument. And the bonus is that we can also, in principle, go to higher wrapping. The drawback is that we are restricted so far to a billion S matrix. Okay, I think I have to speed up because I'm okay. Still have a lot of slides, I think. So now we can try to apply it to generic situations. So first, for hexagons, this type of formula. So first, I should say that before wrapping, there is a closed formula, there is a closed expression for the integrand with any number of magnon on each side here of this figure. And it has a simple factorized structure. Okay, so everything is encoded in some weight that are known exactly. And the only interaction that remains is actually between the two sides here, the green and red side of the figure. The divergences are visible here in the fact that this interaction is controlled, I mean, this delta here as a zero when the two rapidities are the same, the double zeros actually. But we can apply this recipe that I mentioned. So we can cut open green, that is a bit like going a little bit off shell, and apply this recipe, remove the pole and so on. And mathematically, it's similar to trying to regularize product of distribution, so a product that is not very well defined. And what we get is something that will be well defined because of some I zeros that is getting introduced, and also some contact term, okay, that live on this place where the problem sits. And if we do so, typically what we get, so that's an example. If we apply for instance, this connected prescription to the simplest situation with two magnon on both sides, then we will get something here which is regularized with some I zeros, so it's fine. It's just the original object with some I zeros, and something again which is totally localized and comes with a delta function, and which we can think of as being the finite part of this wrapping correction. Okay. So it is naturally seen as well as dressing, you know, whatever we had before with no mirror excitation. Okay, so there is a notion of renormalization, which consists in taking this finite loop that we are getting and adding them up to what we had before. Okay, hoping that it will converge towards something nice. So we can do that in the presence of arbitrarily many magnon in the bulk of the figure. And this way, we will learn about the renormalization of the various weight and ingredients that we have here. Okay? And what we find is that the corrections are very gentle in a way, because well, the text is formed, it's not very transparent. But in fact, if you are familiar to the higher expansion, the Lusher formalism for the calculation of the y function, for instance, then you will immediately recognize that it is almost the same as a y function. So the y function, in fact, is exactly this, with h being replaced by s, by the S matrix. So in some sense, all we are doing here is replace an S matrix, or to be precise, the dynamical part of the S matrix by the hexagon form factor. So dynamical part of the hexagon form factor. So not everything is that simple, though. There is this funny channel B, where the particle, the mirror magnon, is as far as possible from the excitations, the operator here, which is defining a kind of polarization. And then in this case, what we find an additional contribution. We find this cubic wrapping, which is a codimension 2 contact term. So in the end, it is a one-fold integral, which is describing situation where the free magnons here, we started from, the free mirror magnons, have the exact same quantum numbers and rapidities. So they are like some sort of, it's like some sort of free magnon bound state, but a little bit delocalized on the figure. It's not clear where it is exactly. I should say that this contribution is not fully disconnected from that one. This is one fold, this is two-fold, that's three-fold. So it's clear that if you start changing the I0, you will affect the two-fold. By touching the two-fold, you will affect the one-fold. There is a cascading effect. So these things are tied up together. Yeah, it's not just, but we do have the three of them here. That's just a quick comment about the fact that the picture I'm drawing are not quite correct, should not be taken too seriously, just simpler to draw. The cubic wrapping looks in fact closer to this. Okay, we have a magnon that is splitting, there is some cubic interaction presumably somewhere, and it's splitting, going around the operator in the middle and reforming back. Okay, it's kind of reminiscent of Lucian mu term. So what we get then is, after renormalizing, so just assembling the pieces together, is something that looks like a sum of two terms. You know, we have two t's in the problem, and one is associated with positive energy, the other one is associated with negative energy, or vice versa. And there is something good about this, having this combination. So a posteriori, we can try to think about why are we getting this combination, and does it have nice property, and so on. And the short answer is yes. I won't have time to explain, but there is some nice thing happening thanks to the fact that we have these two waves, this small and large solution. But more prosaically here, I just want to mention that it is needed to match data. And here, since I don't have much time, I will go straight to the point. So there is a calculation that was done at 5 loops by Alessandro and collaborators. That precisely observe a mismatch with hexagons and perturbation theory at a place where you will not naively expect wrapping to play a game. So they were considering a particular ratio here, for which the divergence in the numerator and denominator should in principle cancel out. Nonetheless, they found that there is a mismatch. There is this extra piece, which is far from being small and well, clearly not zero. And our prediction fits that, because it is predicting that there is indeed some extra piece that should be added, and which are precisely controlled by these two effects in the bit channel that we worked out. And the calculation is complicated, and we get some ugly beast in the middle. But we see that by adding up the two effects, the ugly piece cancel out magically, and the rest match perturbation theory. There is also a test at strong coupling, but I will squeeze it to nothing. And at the end, I guess I won't have much time, but I will try to flash some UV completion. So I say it's very hard to move to higher order in this business. So we can produce stuff order by order in some approximation, but I don't know how to do things systematically. But we can have a look at what we are getting and see if we can guess something. And by something, I mean something that is totally factorized as simply as possible and kind of TB inspired, like addressing of the original formula, not something crazy, of course. But it might be wrong, it might be simple and wrong. And so the main idea is to keep the original structure, just put some I0 at places where they are needed to fix the divergences, and then correct the weight, okay? A bit like in the spirit of this Leclerc-Moussardou. And we want to correct the weight simply by introducing a pair of dress transfer matrices that captures the wrapping correction, all of them. And our conjecture, which is consistent with what we are seeing in the IR, is that these transfer matrices are very simply related to the y function. So you see the product of these two, t plus and t minus, which is the y function, as well as a ratio, but which is given by something slightly more complicated with the hexagon form factor or hexagon interaction delta showing up here in the kernel. That is, again, that is inspired by what we have in the IR, and that we just want to claim that it is correct. There is also some story about the normalization factor, which is too long to be told here. And we can do some sort of consistency check of this guess. In particular, by looking at how things behave when we do this excited state continuation, when we bring the roots across the imaginary line in the direction of the spin chain kinematics. And what we find is that we are precisely producing what we expect to get from the asymptotic description. So in a way, this guess is consistent with this monodromy that we expect when we move excitation from, when we pull out excitation from the mirror kinematics to the spin shape. In particular, we find that these dress transfer matrices pick up some factors and some usual things that is happening with this continuation that depend on the roots. So the beta roots that we are injecting in the system. But it is also producing the sum over the partition of the roots, which what the experts know is something we get from the hexagon at 3 level. And it has to do with the thing that here we have many layers of contour integrals, that we have to cross. So there are these integrals that are associated with the y function, and then we have this integral in the mirror sums. And the root can cross many of these contours. One of them is a reference, one is plus I0, the other one is minus I0. And this produces some sort of cascade that eventually produces sum over partitions. So it's a good guess for that. I would say it's capturing the essence of the correct structure eventually after continuation. There is a more precise test that we can make, which has to do with strong coupling. So we can do it by considering just the adjacent channel, so just excitation on the 2 sides of the excited operator. And what we will get is the problem we will have the problem that we have to solve is to sum over this, carry out this double sum over these 2 channels, which are weighted by some complicated function of the y functions. It's akin to computing the partition function for a gas of opposite charge excitation with some fugacity, rapidity dependent fugacity, and some type of interaction. And it's a 2-channel generalization of the problem that was considered by Ivan, Didina, and friends. There are many simplifications. It's strong coupling. The interaction is almost trivial, and it's just localized. And all we have to do is actually find, all this place where the interaction localize and form cluster of excitation. The weight, they get extremely simple in this limit as well. By extremely simple, I mean that the phase is trivial. So if I go back here, yeah, there is a piece which is controlled by the y function, and there is another piece that has this convolution, which is a phase. So this phase is subleading a strong coupling. So what we are left with the square root of this combination, which is known as filling fraction. So what we have to do in order to carry a check is compute this integral exactly as strong coupling with this weight and see whether it matches or not the string theory. We find that it's possible to do this, to calculate this sum, this partition function. It's a guess here again. Well, what we did is computed few residues and then extrapolated. And what we find is that we can write it in this concise form with this f here essentially resumming all the residues of the integral and taking this nice and suggestive form that will continue forever. There is a pattern. And it will agree with string theory if this f, this infinite sum, is identical to the sum that we will get if we are switching off all the wrapping correction. So the string theory answer essentially has no wrapping correction in it, in a way, well, we can interpret it like that. So the claim is that the rho here, the weight, must be such that if we remove all wrapping and kill all the rho here, only keep the terms, this is linear in rho. Sorry, the claim is that this should be equal to that. So rho should have wrapping corrections that are just canceling each other such that the end result in F has no wrapping correction. That was not very clear, but I hope you got it. And we can turn it into a hierarchy of equations. So this is an equation for the leading term, for instance. There is a next term and so on. And the equation gets more and more complicated, more and more nonlinear. Okay. And to carry the test, we can just plug our conjecture for rho and also the exact expression for the classical y function that were worked out by Kolya Gromov many years ago. And then we just expand in the wrapping, for instance, and we check indeed that there is no wrapping correction on the right-hand side here. The first equation can actually be verified exactly. We can perform this sum in Mathematica. For the other one, it's more intricate. We cannot find an easy way of doing, but we can definitely do an expansion in the, in the way I've described in the IR regime when rho and t are small. Then we can just plug in some expansion, expand, and check. Okay, and we can do it to very high order. So I believe this should be considered as a check of the proposal. But we don't have a general proof. We just can check. It will be nice, in particular, to see if this very complicated set of equations can be shown to be equivalent to the y system that is defining the y function. Okay, the rest is much harder to check. I will not say much about it. There are a few things we can do, but they are like in small corner, very limited check. Anyway, so here is a summary. So the bottom line is that we can improve the hexagon formula, such as to incorporate wrapping corrections. We can do it reliably by drawing inspiration from what people did for local operators, in particular this Leclerc-Musardo formula. And this way obtain information order by order in the IR expansion, in the wrapping expansion, or in the Lucia expansion if you prefer. And that will give us, this way we can get a glimpse at part of the answer and try to see some pattern. And from what we have found, well, we could guess. So first, we find that there is a lot of similarity with the expansion of the y function in the TBA. Perhaps this was expected. But anyway, this was a motivation for us to try to do some sort of, to play this game of resumming, exact resummation, or I should say, to conjecturing the final answer. We also find this new bit, this cubic wrapping, which I've mentioned is important to check. And so again, with all of this information, we found this conjecture, which only apply, I should stress, to this the simplest structure constants, where one operator is non-BPS, the other two being protected. It passed non-trivial check, but we don't know how to derive it. Now, for the future, some other important question to address will be, now that we have a finite formula, we can look for simplification in this mirror sum and possibly hope for something even nicer, something that will reveal the Q functions, which give a better encoding of the wrapping correction in general, and that could also be possibly easier to use in practice for practical calculation than this infinite sum over mirror correction. Thank you.
Okay, so thanks a lot, Benjamin. I'm so. Okay, so there are already questions online. I don't know how we proceed. Can they speak directly?
Yeah.
Should we just go for that? Sorry, my background is a bit weird. Greetings from London, Benjamin. Nice talk, thank you. I don't know, can you hear me or not? Blink if you can hear me. Well, I can see you blinking though. Ben, can you hear me? Yes. Okay, so my question is, how much of this survives in fishnet limit, where we can have a chance to understand on more like basic level how this could work in relation to your last point?
Yes, so I heard the word fishnet, so I guess it means whether it's possible to get something in the fishnet theory. And yes, there is a fishnet counterpart of this formula. I mean, this guess for particular states. Yeah. So I'm just trying to, well, I don't think there will be so much simplification. Of course, there are some pieces of the answer that will drop out, like this cubic wrapping. All of this will be absent in the fishnet theory. We will just have this adjacent channel is the one I'm thinking about, you know, with two operators being protected, kind of, you know, open string light operator with no single trace condition and one single trace in the middle. Okay, then we will just have wheel around one operator. And these two adjacent channels, they will reconstruct this wheel in the 3-point function. So we could write something there, and then yeah, then the problem is indeed how to resum this, how to carry out this sum over the mirror correction, and possibly do some check in situation where formula are known, like the cases you guys worked out for length 2 operator, for instance, which is known exactly, I believe. So yeah, the formula exists, and possibly, yeah, it's a good start to look for simplification. Yeah.
Thank you.
Okay, then Volodya, maybe you said.
Hello. Also, greetings to all the participants on Zoom and who are in physical presence there. It's a pity that I cannot speak from directly there to you. So my question to Benjamin, there was a formula on one of the transparencies where it was literally integral over 3 transfer matrices, T functions. Of course, there are some up to the details which I'm not sure I remember, but it seems to be the most transparent for me formula, and it seems to be first of all finite. It doesn't have any sums. You just have transfer matrices. But of course, probably what you mean by sums, it's the calculation of these T plus, T minus, T plus minus. Yes. Otherwise, the formula is complete. Do I understand correctly?
I'm not sure I understood your question.
So this is also the exact. This is supposed to be exact formula if you know the exact objects here. Yes, or not?
So the claim is that the initial hexagon formula. Sorry, I was a bit fast, I guess, on this part, which is important. The claim is that the original hexagon formula is correct after adding some I0 to remove the problem, the original problem, and also including wrapping correction through this dressing of transfer matrices. And by dressing, I mean essentially defining this T plus and T minus in such a way that their product gives this ratio of Y function, and their ratio gives this expression. Okay, so in the end, this is meant to be exact. This is meant to be exact, but
Hello? Hello, hello?
yeah, we could not hear you, Volodya.
Yeah, it's not my fault. Do you hear me now? Hello? I was muted. I don't know why.
Yeah, now you're not muted anymore. You can talk. Yeah.
I didn't do anything. So all these functions y, say at the end of the page, they are not pure TBA quantities.
No, these y functions they are your y function. Yes.
Yes. So then, in principle, it seems that it expresses all these formulas on this page express structure constants through standard TBA quantities. Yes.
Yeah, it's that's the idea. That was the goal. Yeah.
So this is the conjecture up to this
but
denominator.
okay, I think you what can be misleading here is I'm writing this formula as if it was a single integral, but it isn't. So
Yes.
this is just to simplify my life, but this is really like the partition function in the way I presented it at the beginning. So it's an infinite sum of integrals.
I see.
It's not exactly what you want, I believe. It's not just integral of some Q function, but
Some
possibly it is equivalent to it. If it's just completely unclear to me how to simplify this sum.
I mean, integral over 3 characters, then quantum characters. That was always my dream.
If there is something better, possibly it may be derived from this formula or not. I don't
And
know.
the way to integral of Q functions is also quite long. Yes, it's not that you just plug here the expressions for transfer matrices in terms of Q functions and you get it. It's more complicated. Yes.
No, I don't know. For me, this is more like the next step. So how do you, now that you have something finite, that was the very last comment on my slides. Now that we have a finite expression, what can we do with it? So in practice, if you want to evaluate it, it's quite a pain to use this y function and expand and so on. It's very complicated. So we probably want to go now to the Q and see. Possibly something nice will happen for this formula when we go to the Q, and we'll suggest some, resummation path or something next to do. Or I don't know, possibly it's just, some way of writing the answer that is just like some, I don't know, will not necessarily connect naturally to the Q function.
Thank you.
Okay.
Hi. So maybe it was a bit related to what Volodya was asking because I might have missed it. So the idea is that this is still a prescription that will regularize everything, but is still in the framework of a particle by particle expand. I mean, you're still expanding over the number of mirror particles, right? Okay. So in particular, you have to sum over them, and in some cases, well, I guess maybe not in this particular case of the BPS, no BPS, but I guess in some cases you could also have that for a given loop order, you would have to consider infinitely many particles, right? I mean, you still have to do all these sums over particles essentially to. So
it is exactly the same structure as before. Just change, the ingredient inside each. So the problem gets a little bit more complicated now because you have this integral that has these t's. The t's themselves are given in terms of the y that have integral in them inside. So it's more complicated nested object. But the logic is the same. We are assuming that the structure stays the same as before, but we just have, to fix the ingredient.
Okay. And do you think that this can give more insight on how to sort of avoid expanding over mirror particle at all?
I guess it's related to Volodya's question, which is now, how do we get rid of this expansion? How do we get rid of these mirror particles and some, which are a pain? And how do we get something more concise, like what people hope to get from Q functions, which may presumably be simpler. And that I don't know, because for me it has to do with resummation of mirror particles. So there has been some progress, as you know, on this side, like in resumming in some situation for 4-point function of large charge operator. So we may hope that possibly there is like some structure in it that will allow us to get something even more nicer. But it's not clear how to proceed. I guess at some point someone has to try something and see where it goes. But it might also be just what it is, something similar to the Leclerc-Musardo formula for the 1-point function. And we know that in the problem, in the context of 1-point function, sometimes you can do better. You can get well, you should ask Zoli, but Zoli can do better. And it's not clear how to go from one to the other. It's like two orthogonal way of thinking that should agree in the end, but it's not clear how to jump from one to the other. Could be the same thing.
So
this plus minus I0 seems a bit suspicious to me. So can you write the Leclerc-Musardo formula in the same spirit with plus minus I0?
I haven't thought about it, so I don't know. But I guess, you know, the problem is, okay, Leclerc-Musardo is also very diagonal. And now I'm talking about something that is very off diagonal. So could it be also that, you know, what you find suspicious is just a bias based on the fact that in the diagonal setup, we might not have this plus minus, or they might just be replaced by something you like more, I don't know. But yeah, I'm not saying that they are essential part. I mean, of course, we need this plus minus I0 here to make sense of the integral. Otherwise, I don't know what to do. And that seems to result in this two transfer matrices plus and minus. There is a relation between the choice of plus minus and the prescription. There is some sort of connection among them. And yeah, well, maybe there is another prescription that will just erase this, and we just pick this way in particular at some point and stick to it. But
I just remember some old way of deriving the Leclerc-Musardo formula using epsilons, basically. Just one single epsilon never give the right formula. You had to use many different epsilons and then really go to finite volume to regulate, to get the subsequent terms. It was impossible to get it in infinite volume somehow.
Okay, you're talking about you're not talking about this I0 here. You're talking about something else. You're talking about when you.
Maybe I haven't got completely this I0. So.
I think you're talking about this, no? How do you get something finite? How do you get something finite out of something that may be possibly divergent?
Yeah, I expected this is same I0. Yeah.
Well, it's not really the same. I mean, this I0 we get because we start with something that is fine, but which has complicated contours. Like some contours are in the lower half plane, some contours are in the upper half plane. And so the first thing we do is to move all the contour on one side. And because what is left behind, which is just a residue, is a piece that is singular. So we are extracting the singular piece this way. The rest we call bulk, we forget about because it's fine, okay? And then we treat the divergence and we get what we get. If at the end you want to rearrange, oops. If at the end you want to rearrange things in a different way, you can, but you can imagine that algebraically it's getting very complicated. You have these integrals that are coupled to each other with plus and minuses, plus and minus zeros, and just moving the contour around sometimes it's a mess when things connect to everything. So, but I'm not saying that they are the same as if you ask me what is a prescription for extracting the finite part of the result if you have more magnons. I'm not saying that you just need to pick some residue. Or I don't know. I don't know what you have to do. It's something more complicated.
Do you have a general prescription how to get the finite part out of?
No, we don't. I mean, well, I don't know how to answer this question. It's not an explicit expression. What we have is, well, we don't have anything except that we know we can rely on this type of object here. So this object we think is under control. And so we should get something finite out of it, okay? But that may be extremely complicated in the end, you know, with a finite part being, you know, take this object, remove the pole, add the delta function, do this, do that. So the list can be very, very long. We just hope for the best. We hope that in the end it will collapse in this nice object that we conjecture out. But there are only small situation when we can do checks.
Thank you.
Okay, so we only have time for a short question online.
Hello, Ben, can you hear me?
Yes.
Yeah, okay, it's Anton speaking, and yeah, hello everybody. Sorry, Ben, I think I have a quick question, maybe one along the lines of what Zoltan was asking regarding this. When you talk about Leclerc-Massardo formula generalization and this going to higher orders, but is there any indication how you can extract these extra contributions that you will find in distinct, like if you go order by order, is there a possibility to identify the pattern? How do these multifold contributions develop? Or, I mean, namely, it is in order to achieve, I don't know, to all order.
I'm sorry, Anton, I did not get it. Somebody got it? Oh.
So the question is regarding these high loop contributions, or maybe all loop potentially. When you mentioned this IR order by order possibility, and you mentioned that's a complication. So the question is, can you go this way, and is there a chance to identify the pattern? How do these extra contributions that which you marked in red develop, or maybe find the general formula for them?
Someone got it? Because I don't know if it's related to the fact that it's...
I think you were showing...
Anton, the connection is not very good. I'm not hearing you very well. Oh, I don't know if it is because I'm getting the sounds from different places at the same time with a small delay, but I'm not understanding the question.
I mean,
yeah, can you write it in the chat quickly if it's not too long, please? Okay. Yeah, we have IR complications everywhere.
Can you see now?
Where is the chat? Where's the chat?
Oh, sorry, I should correct. I mean, you have been showing these contributions in red. Can you hear me at all, or is it really bad?
I can hear you, but I don't see the chat. I am asking.
I mean, yeah, okay, but maybe I can write to several, but there was terms.
I don't know what to do. Where is the chat?
Okay, Ben, can you get to the slide where you have been marking the terms in red?
Chat. Ah. The term I've shown in red.
Yeah.
Which term? In the weak coupling?
Yeah.
This one?
Yes.
Ah, sorry. I was kilometers away. I did not think you were talking about that at all. Okay.
Sorry. And I think maybe even one slide above.
Well, they are ugly. So you really want to know what they are?
No.
Really ugly.
I'm not. No, Ben, I'm not asking what is their form. It eventually doesn't matter since they cancel. But I think before on the previous slide, one slide above.
Mm-hmm.
No, maybe here.
More?
Yes. No, I think below now.
More? I don't know. Don't understand.
No, down. Yeah, here above.
This one, yes?
One more above.
One more above.
One more. And from this one more.
This one?
No, I think one more.
Sorry. Are you sure there is no red before?
Yeah, I think that you were showing there were clearly two terms that you were showing in red, and I was wondering if you understand how do they develop it. What? Okay, is this really the only one?
Well, there is nothing before except this result, which is the field theory result, and there is no red. Yeah, sorry, Anton. Maybe you should ask offline. If you write me, I'll be happy to answer the.
Yeah, we can discuss this on Slack. But I'm wondering how does it develop at higher orders? Okay.
Well, that's an interesting question. In fact, they're ugly, but I think it's possible to write something. It's just they are more complicated objects.
Yeah, but
that are not just zeta function, but also psi function and this type of thing, which are, we don't expect them to survive, but they are there.
yeah, sure. But at higher orders, you expect cancellations always to hold?
Well, if they don't cancel, there is a problem, yes. So usually when you see that something is not canceling, it's hinting at the fact that you are missing something, yes. You should be, maybe you are missing some correction. So it's a kind of check, qualitative check you can make of your formula, assuming you can calculate them to that accuracy, whether the ugly part cancel out. It's really a powerful consistency check. Usually if you write a guess and it's not conform with this zeta pattern type,
Yeah.
you can throw it away, or you have to fix it. For a while, we knew this piece here, and but it did not match data, and then we found that one. Well, we realized we forgot that one, which was a very small effect, and fortunately, it was such that they cancel out precisely. But if it fails at higher order, it means that something else is missing.
Yeah, okay. Okay, I will leave the rest of questions to the Slack. Okay, thanks.
Thank you, Anton.